Stefan Thurner is the president of the Complexity Science Hub in Vienna, and complex systems science physicist, I think is the right sequence of words. You've done a lot of work. You're at the Medical University of Vienna, but this complex systems science, complexity science hub is in Klosterneuburg, if I'm well informed, in a very No?
It's in the center of Vienna.
Oh, it's in the center of Vienna. Okay.
Yeah.
But it's a whole, it's basically like a group of groups in essence, right? So there's many different research projects going on with different configurations. So very similar to like a large Max Planck Institute in essence. Is that true? Or?
Yeah, like an interactive Max Planck Institute.
Nice. The other thing that is important to know about Stefan is he's also an external faculty and longtime affiliate of the Santa Fe Institute, which is the US sort of node of complexity science beyond physics. There's a whole origination myth going on surrounding Murray Gell-Mann and other people who were involved with Los Alamos Laboratory and board that they have to do nuclear physics. But the interesting thing about Vienna is sort of, one could say, also another route of complexity science, which is the European route, which is important to underscore, because if you take a look at who is actually grasping culture as a complex system, then you will see that the US hierarchy, as outlined by Philip Orr-Anderson and Morris Different, stops at sociology, while the Austrian branch takes in what Rupert Riedel called Kulturwissenschaft strictu sensu, which means basically stuff with objects, churches, Gothic ground plans, harnesses of people wearing in the, knights in the medieval ages, and other stuff such as art history. And so that is a very interesting kind of connection, I think. Stefan has, in the last couple of years, written two things which everybody should know. One is the Introduction to the Theory of Complex Systems, Oxford University Press. So that is one of the introductory books. If you want to get a slight, sort of a simple on-ramp, you probably start with Complexity Explained, the online tutorial, or Melanie Mitchell, I guess. But if you want to get serious, you need to read Stefan. Was that a good intro?
If you want to get bored, I guess.
Okay. And then you also wrote something else that's really interesting in the European Physics Journal. You wrote an article called Complex Systems, Physics Beyond Physics, which actually contains a chapter on complexity in humanities, which also is quite cool. And this is sort of the topic of our sort of resonance. There is two things going on here. In cultural data analytics, CUDAN, the project, we're 10 people spanning the full spectrum from cultural semiotics, cultural history, creative industry studies, like cinema tickets, stuff like that, and computational linguistics, generative art with machine learning, policy studies, what else? Cultural semiotics proper, stuff that is more computational social science, like in the overlap with critical media studies in one case, in the other case, proper like Instagram and geographic images plus machine learning and stuff like that. So there's a very wide spectrum. But one thing where we could extend, I think, is the area of sociocultural complexity science. And let me rephrase Rupert Riedel, strictu sensu. So basically the physics that's behind it, behind multidimensional embedding spaces, behind time series, behind the networks that underlie it and stuff like that. So I think there's a really interesting kind of resonance going on, which one could sort of maybe summarize in 5 lobes. You have this cultural data analytics thing, which is actually a first bridge of humanity and complexity science, computational social science, the socio-geographic realm, dealing with text, literature, linguistics, history, dealing with objects, and in particular, obviously, most of the time, visual stuff, which begs machine learning, deep learning, and all that stuff. And then there is the sort of uncanny topology, mathematical quantification, network science, complexity science in the background, which is maybe the last thing one thinks of, but probably the central thing we should think about. So we had a conversation before Christmas where we said, wouldn't it be nice if you could fly the CUDAN team to Vienna and your team over here to mutually hang out in either the Heurigen or a beer garden in Tallinn. We should still do this after the pandemic. So we then decided to start slow via Zoom. And so yesterday you sent us the topic you'd like to talk about, but I just give it to you and you can introduce that yourself. So it's a great pleasure to have you here. And so yes, please introduce us to your view of culture.
Thank you very much. Great pleasure to get to know your group a little better. So yeah, so that's true. We're at this complexity science hub in Vienna. We're a little bit biased towards mathematicians and physicists and computer scientists, not many artists, even though we have a little art program. But don't be afraid. I will not talk about anything that is more complicated than a triangle. That's all you have to know in terms of mathematics. If you don't get certain things on my slides, then don't worry. It's all just about triangles. And interrupt me at every second if something is not clear, or if you think you would like to understand a little bit better what I'm talking about. Interrupt me. Since a couple of years, since 10 years or even more than 10 years, we're looking at societies, and we're taking an angle of societies that I think a guy more than 200 years ago, Auguste Comte, wanted to do. This is a poor character in history. He wanted to do a physics of society around 1810, something like this, where all these great physicists discovered how to really popularize physics and become super famous and successful. And this guy said, let's do the same thing with societies. And he didn't have a computer. He didn't have a statistical mechanics. He didn't have mathematics. He didn't have statistics. So it was just a dream, but it was a very good dream. And we're getting closer to this, to understanding societies as a very natural phenomenon, which maybe we can sooner or later, and don't get me wrong, I'm not really believing in, but that sooner or later we can formulate a natural science out of it. And if you take this a little bit serious, you can make amazing statements. And I would like to show you one of these statements. And for this, I would now share my screen.
Should be possible.
Yeah. I think it's this.
Yes.
So
if you do, I think Control or Apple L before, if you make it full screen before you share the screen, we can see only your slide.
I will do that. Yes. God, I have so many windows open.
Welcome to the club.
I think I'm too stupid to do that, but try it again.
Then let's just continue as we did. It's
Yeah.
okay. Maybe with one screen, it's maybe hard to do, actually.
Let me see. I used to be able to do that. You see it now on the whole screen?
No, we see the still the same thing. But it's okay. I think it's large enough. We can all see stuff.
I see it on my screen, the whole screen.
Okay, maybe you have to change the view once, and then it becomes. We're still the 3 problems. You can see that.
You see the 3 problems. Yeah. Okay. Let's start with the 3 problems. In current society, I think we have 3 things going on that are going on very slow. One is social polarization, meaning that parts of society, large parts of societies, are fragmenting into 2 blocks. There's social fragmentation, which is a very different phenomenon, maybe even more scary than polarization. That society is breaking up into lots of different bubbles and little small groups, where within the groups people like each other, but between groups they hate each other. And the third is formation of parallel societies. All 3 of these processes are threatening civil society. As you know, in democracies, we are finding compromises all the time. And for this, it's necessary that people, and all people, more or less, have to talk to each other. And if you have polarization, fragmentation, or parallel societies going on, there is no more chance of collective opinion formation processes that we like so much in the free world. So what I would like to focus on is social fragmentation. That's maybe the hardest one to understand. And we want to understand what's happening based on some very basic demographic trends, based on new forms of communication and interaction, how people talk to each other. That has changed dramatically over the last 30, 40 years. And we would like to understand what's going on the basis of very fundamental human forms of interaction. So basically homophily and social balance. Are these terms familiar to you, or should I say a few words about it?
Maybe say a few words about it. We're still at the 3 problem slides. So if you, maybe exit your full screen and then just click on the little bar so the toolbar disappears on the right. Like there's this the vertical bar left of optimized PDF. Yeah, whatever. Sorry. Nice. Okay.
Yeah.
Yes.
Now, do you see what is a society?
Yes.
Okay.
And we saw it change.
Okay. Okay. So I say a few words about these fundamental forms of human, what humans do. They are homophilous. What does that mean? People try to change. No, people try to be similar than others. If you're in a group of people that are very different, and if you cannot escape this group, you will change your behavior, your opinions, your ways of interacting, your social ties, etc., to become similar to that group. That's what humans are doing over and over again. No matter where you look, they're doing this. And people care about social balance. That's a thing we'll talk about a lot. That is, that if I have two friends and if I know that they are not friends, I will introduce them, that they also become friends. That's yeah, in a nutshell what homophily and social balance mean. Homophily means become similar to the other one. Social balance means think of social triangles. So what is a society? And this is what people in this complexity science field, many of them believe that a complex system is always of this form. It always looks like this. It looks like a network. You have dots here. These are people, for example, and there's links between them. Links are all sorts of interactions you can have with different people. So you can be friends with people. That would be a line, or dashed line is that you dislike others, or that you are trading something with them, or that you are giving them a present, or if you're killing someone, could all be different forms of interaction, positive, negative, or of no value. And what is important is that every person, for example, has a property, or has properties, many properties. So the shape here could be, I don't know, if it's if you're poor or rich, and the color indicates that you're maybe male or female, or so every person has a whole set of properties and a whole set of interactions with others. And both of these, the properties and the interactions, are not fixed in time. Both of them are changing. And the properties are changing somehow as a result of the networks of your links, and the links are changing somehow as a result or a function of the properties that people have. So you have this chicken egg problem. The network influences the properties of the individuals, and the properties of the individuals influence the network. That's what we then call a complex system, or a co-evolving multi-layered network. And that's a surprisingly simple definition of what a complex system is. Yet, all the properties, these literally thousands of properties that complex systems can have, come just out or emerge from this very, very simple conceptual thing. You can write this down in equations, and it looks like this. Don't get confused about this. But so I switch back to this. I can say everything with this picture. What we call big data today is that we just know about the properties of individuals. For example, we know all the bank accounts. So not I, but it's written down somewhere. Banks know it, or central banks know it, or maybe the financial office of your country knows your bank account, or every individual, or how many children you have. Someone knows that, or how many telephone calls you make. This is known somewhere, recorded somewhere. So we know, or we as mankind know a lot about the properties of these complex systems and the interactions. Everything that you can store in a relational database is a link in such a network. Yeah. Interrupt me if you disagree, or if you would like to comment.
So maybe what you just said, that's very interesting, because lots of people in our group work with analyzing databases, ripping them into pieces. Right. And sort of my message is that exactly what you just said. It's just nodes and links.
Yeah.
Or not really nicely explicit made. Sometimes it's not really nicely explicit. If you got tables with lots of columns, it's a little harder, but still you could theoretically decompose it like that.
Right.
But that's more
And what's
restricted statement than saying society is like that, which may be more complicated, continuous, for example, stuff like that. But
up to now we had no chance of seeing these links and these properties. We knew our families, our friends, our colleagues at work. We had a little bit of a concept of what these properties and links of our neighborhood looked like, but not of the whole thing. And that's a game changer today, that we can map a society in terms of its individuals, their properties, and their interactions. And I think that's what we call big data, that we don't have any holes in this view anymore. So we're not there yet, but we're getting closer and closer and closer. So what we're doing at the Complexity Science Hub, for example, is that the properties of these nodes are the healthcare states. So how healthy, what kind of diseases you have right now, and how this changes over time. And from this, we try then to develop methods to predict what kind of diseases people will get in the future, depending where you are in this kind of network. Okay, so this is the kind of social science we would like to do. This is very different from what other social scientists have been doing since 200 years, by typically asking people about their opinions and feelings in questionnaires on certain, and from this guess on certain interactions and states of human society. We're not asking people, we're watching them. We watch what they do. We don't want to know how they interpret what they do. We just observe them. It's very different. We don't put in any bias. We don't interfere. We just passively look how humans make decisions. And every decision that's worth anything results in a link or in an interaction with another person or institution. Okay, now I will say he's crazy. He's a surveillance fetishist or something. Let me tell you what we did. We happened to own a computer game. It was the biggest computer game in Europe 15 years ago. It was programmed by a PhD student of mine and his friend. It's called Pardus. It's still alive, the game. It's tremendously old-fashioned, but it's still played by a couple of thousand people. And at its best time, there were about 500,000 people playing it. And so what you do is you are born, then you get the spaceship, then you live somewhere in space. You can go to what you find out is that you are poor, so you have to find a job. Then you find a job, then you earn a little bit of money, and then your social life starts. You meet other people who are also working and trying to spend the money that you have earned, and you can either consume certain things, or you build up a business of your own, or you make a big business with other players, or you become a pirate, or you become a politician, or you become a scientist, or you organize as a police or something. There's many ways you can do in how you can spend your life in this game. And typically you're doing many things at the same time. So you're producing things that people need, or avatars need for a living. So you're producing things, you're distributing things and trading things. You make profit from your economic life, and you're buying typically status symbols. What people do most is they buy new spaceships. You don't need a new spaceship, but you always want to have a shiny new one. That's where people spend most of their money. It's completely absurd, but it's a big driving force. When you meet people, you start talking to them in private. There's a private channel. Then you can also write something like newspapers. You can open your news agency. You have forums and all ways of communicating with other people. And you can also, and this happened in the first years of the game, people explored the universe, mapped it, looked how it works. People found out everything. So there was a science of the game even. So in the game, immediately hierarchical groups were forming, political parties, cartels, a banking system developed, a court system developed, all sorts of friction and conflict arose on a local level, that people were fighting each other, but also wars between different zones in the game, where then 10,000s of people tried to destroy the infrastructure of other 10,000s of people for months and months. And you cannot really die in the game, but you can do lots of destruction to the things that you build up. Okay, so this is a very open-ended second life, kind of. No one tells you what to do. There's no rules, except you cannot be racist or sexist, otherwise you get deleted, and you can only control one avatar, not more. Otherwise you get also deleted. So this is a space monster that exists. It's classified in a biological scheme. So everything is studied by the players. And the fascinating thing about this game is that we know everything. And by everything, I mean everything. Everything every player, every of these 500,000 people ever did. So where they moved, what they did, what they talked, what they were exchanging with others, what they were, how they were interacting with each other. Every time they learned something, we record the improvement of the learning, or if they forget something, we know everything. And that's maybe the first time that about the human society, one knows everything. And with this, we tried to do, again, social science. So, and with this everything, now I go back, I hope you can see that. I mean this, we know this at every second in the game, now for 15 years. Okay, so I show you a tiny little fraction on one day. The green network that you see, this is the friendships of 100 people that were picked out here. You see who likes whom from these 100 people. And the red arrows are enemies. So these people don't like each other. And it's always from one person to another. So you will see little arrows. You see one person who everyone hates, or almost everyone, or many people. And if you just see how if you look at the network, the red one and the green one, you see they're very, very different. And on the right is the same people, and it shows how they were communicating over a month or so. So every time they talk to each other or send an email to each other, there's a line. So the right one is the communication network, the green one is the friendship network, the red one is the enemy network. So if you're a friend, you cannot be enemy. So this is exclusive. So at every point in time, we know how these networks look. And yeah, this is, if you have a network, you don't want to always draw these kind of things because they tell you pretty much nothing. So you have to quantify and distill numbers out of it. And with these numbers characterize the network, and from these you can understand if a network is, I don't know, effective or robust or stable or resilient or whatever. It's just to show you that we have many dozens of different numbers that characterize these networks, and that we know at every point in time. Okay, so from these networks, we wanted to convince sociologists that we can do exactly what they were thinking one should do. So a very famous sociologist is Granovetter, and he said that you can, if you knew the network, you can measure the strength between people, how much attracted they are, or how strong their social relation is. So he just spelled it out and said it should be like this, and we can now prove it. So you see this statement by him that the degree of overlap between two individuals is proportional to the strength of one another. If you know the network, you can quantify what he means by overlap, and then you can measure if this overlap really is related to, for example, how often people talk to each other. And not bore you with the details. We measure it and measure it and measure it, and then we come up with exactly what this guy said. Namely that the strength is this W weight between the two people's relation, as the strength of a relation, is 1 divided by the betweenness between people. And there's these funny numbers, these exponents 2 and 3. You need those that you can that you can explain the empirical facts that we find. So yeah, I don't go into the details. Yeah, sure.
Sorry, can I ask, you mentioned that overlap, but can you explain exactly what the overlap refers to?
Yeah, sure. So you have two people, I and J. Look at this left kind of little network. I and J, they all have friends. Everyone has 4 friends. And the friends don't talk to each other, the friends of I and J. So the overlap is 0. On the right thing, you see I and J, again, they know each other as before, but now also their friends are talking to each other. Their friends also are friends. There you have a huge overlap. And if just a fraction of your friends, if just 20% of your friends are talking to the friends of your friend, then your overlap would be something like 20%. Or it's now just very roughly, the overlap is this formula here. But it's more or less what I said.
So based on shared connections, is that correct?
Based on shared connections, right.
And more informally, the notion he carried was like that these weak ties, which connect you indirectly, seem for some reason to be more important than the direct links in essence. Which, if you just filter them out, if you only take the strong communication links, you would miss them. So he said, like, all these, the large number of links that have low weight are just as important as the links that are frequent and have high weight, right? Isn't it?
So this is another statement that this same guy said. So if you have 2 communities in a network, ones are the soccer players, the other one are the stamp collectors or something, and they typically don't talk to each other. But those people that do talk to each other, in this picture here, there's 2. Only 2 talk to each other. They are extremely important for the coherence of the entire society. So, and these weak links, it's weak because it's only 1. He called bridges, and said that bridge is never a tie, a strong tie. Bridge is always very brittle, that can break. And then he came up with a whole list of things why and for what reasons these bridges are extremely important. And we can quantify this bridginess, and we call that B. We measure this B, and we measure the overlap as a function of B, and then we find this top picture here and see that this is very regular. And the lower picture shows the weight. This is how often people talk to each other as a function of the overlap of the weight. It's another very regular curve, this green curve. And if you take both curves, so the top curve was this B is equal to 1 over overlap to the square, and the other one was W, the weight is proportional to overlap to the third power. If you do the algebra, you get this red formula, expressing the strength of a relation between two people becomes a function of this B. And this B, to compute the B, you need the entire society to compute it correctly. So this is a highly non-trivial finding, namely that your individual strength of friendship to someone else depends on also these weak links. And very, even though this seem completely irrelevant, this is a driving factor. We can even do more crazy things. We can look at just look at the center thing. His people, they are separated by little by a distance. In the game, they also have a distance, and people are exchanging things, exchanging like emails or presents or and by doing so, we ask, when people talk a lot to each other, do they get closer to each other physically? Do they approach each other sooner or later? And they do. And if they do that, you can measure the force between people as a function of how they interact. So this is more or less exactly the same kind of thing that Galileo was doing with planets, or with stones falling from the church, or what Newton did in understanding how planets are attracted to each other and to the sun. And he was measuring, they were measuring forces. We can do the same with people if we know where they are and how they are interacting. So there is an attractive force of communication. I think I will skip this kind of thing. I'll also skip the gender differences.
I wouldn't.
You wouldn't?
We have a lot of people who are really interested in it, particularly
Okay. Okay.
wants to know that, right?
Okay. No, I don't skip it, but then I have to explain.
Okay.
I don't have to explain this. This is just a curiosity that a crazy English psychologist came up with maybe 30, 40, 50 years ago, Robin Dunbar. I got to know him and was very fascinated by his most famous, by second most famous finding. His most important finding is that human societies typically don't get larger than 150. 150 is the Dunbar number. It's all sorts of reasons. The second most important finding of his is that people, if you look at the group sizes people are making, you find that groups of 3 people are totally overrepresented. Then 4 people, 5 people, 6 people are not so frequent, 7, 8 also not. Then you find that groups of 9 are also overrepresented. There's many more groups of 9 people than there are of 8 people or 10 people. So 9 is 3 by 3, 3 times 3. And he also finds that 3 times 3 times 3, 3 to the third power, 27, is also overrepresented. And then 3 to the power of 4 also. And that's done by numbers, not the number, but numbers, plural. And he also found this in dolphin schools and primates and military organizations or human groups or groups of Homo sapiens before they settled into cities. And now we find the same thing in a computer game, but it's not 3, the magic number, it's 4. So super cool. So groups of 4 are overrepresented, groups of 16 are overrepresented, groups of 16 times 4, etc. So you see these spikes here in the right picture, which is really, no one understands why. So you can become famous if you find a reason why we are doing this as a species. In the game, you get the gender when you start. You pick a gender, and the game is a little bit sexist in the sense that you cannot change your gender. That's better in the real life. So once you have it, you stick with it. But what is better in the game than in real life, you can choose from a different species. So, but there's always male and female. Now we looked at, again, the networks, many different networks, friendship networks, communication networks, trading networks, networks of enemies, networks of people that attack each other. And it's also an ugly thing that you can do in the game. You can put a bounty on someone else's head. I can pay you to hit someone else. So very politically incorrect. And then we check what is the differences of degrees in these networks. So this is 6 different networks. Do you know what the degree is? Should I say something about the degree? The degree in a network, there's just dots, nodes, and links, lines, right? The degree of a node is how many links it has. So in the communication network, my degree is the number of people I talk to. In the friendship network, my degree is my number of friends. Okay, so what we look here is how many friends do females have minus how many friends do males have minus how many friends do females have. If that is 0, as we find here, more or less, then males and females have the same number of friends. When we look at communication partners, number of communication partners on average of males minus those of females, we find a negative number. We find something like -4 and -5. That means that females have 5 more people they talk to on average. So if males talk to 10 people, females talk to 15 people. Also in trading, the trading networks, females have more trading partners than males. And for these negative interactions, like being an enemy or attacking or bounty, males and females are more or less the same. Then in networks, a very important number is not only the degree, but also the clustering coefficient. What is that? That is in how many triangles are you embedded? In how many triangles, in what percentage of triangles that would be possible in your local neighborhood are you actually embedded? So it's a, yeah, please.
Can I ask? So I would imagine that this the magic shaped triangle would refer back to the Dunbar numbers based on the triads appearing more often in real society. Wouldn't you change that to 4 when you look at your game because you saw more occurrences of 4s?
With the triangles, you cannot explain the Dunbar numbers, or at least not in a simple way. People have been trying to do that for at least a decade. So it's a nice idea.
But the other way around, you can, like, basically, if you're not doing the Dunbar numbers, but if I understood correctly, your question was, shouldn't you look at quadrangles or something like that, which you implicitly do when you look for triangles, because if you have 4 people, there's a number of triangles you can draw. You see, like between 3 people, there's only 1 triangle. Between 4 people, there is more triangles you can draw, right?
Right. You can decompose a 4-edge thing into triangles all the time. So the triangle is the next most fundamental thing to a 2 relation, a dyad.
Yes.
It's just the next level. And if you would jump from the dyad just immediately to the quadrangle, or then you would leave out 1 step.
Jan has a question.
I have probably a similar question about the protocols of the networks, if they are actually known for both players, because the programmers or the developer of this game probably designed the game based on the Boolean logic and the computer math, meaning, let's say that everything works better when it's in power of 2. And if there is a crew of the cabin, it should be like 2 to 4 people, then users would just abuse the system to its maximum. Let's say filling the cabin into 4 people.
Now, the programmers did not put anything into the game that biases group size. It's open-ended. So that's not, there's no, if people meet, if they interact in one or the other way, so there's dozens of ways you can interact. It's not only these 6 types that are shown here, there's many more. How people decide to interact, and by doing that form these networks, is completely open to people and chance, and in no way influenced by the game designers.
Okay, I mean, it's just in a car, there are 2 people in the front seat, and there is no way you can put there 3 people, right? So if you would have networks of couples driving the cars, there would be a power of 2 always.
Right.
Because there is a protocol.
Right. No. You can load many people into your spaceship. You can have many people fit into a city. A city is just a planet where you add satellites that you can build, like houses. There's a very dispersed street map. So these are wormholes connecting planets and cities. There's no limit of how big a group can get.
Okay.
Some groups from political parties, they have 10,000s of people. But there's also a huge number of just 2 friends roaming around the universe together most of the time. So it's a huge spectrum of possibilities.
Interesting. Mark has another question.
Yeah, I thought we might as well continue with questions. So about this, you have the bridges, and then you have this kind of overlaps. And would you agree to call it actually kind of social context? and it's kind of mathematical version of social context that is important. Then
nice that you asked that question. What is social context? So what we have here is a number of people, and they are connected not only through one network, but through, let's say, 20 different networks. When you look at how people are, for example, talking, that's the communication network. You cannot take the conversation network out of context of I don't know, of who are friends, for example. So you have to explain or to understand one, the communication network, you need the other layer. You need the friendship network. And you also need a third layer, who hates each other, who hates whom. So you have now 3 networks, where 2 are necessary to understand the third one. The 2 are the context of the first. That's the cool thing about multi-layer networks. The different layers form the context for the layer you're interested in.
It overlaps pretty well with the semiotic perspectives of the minimal the systems of understanding. You need to have 2 systems basically to create some sort of meaning, and it actually seems to connect with this idea, I think, that you have this multiple layers, and then you can actually get this meaning.
But there is nothing else. If there is meaning, it's between the layers. There is nothing else. If you look at the system, unless you believe in God or ghosts or spirits or something like this, then you can explain more. But context is always connecting the same set of people or institutions or cells or animals or banks or whatever into other sets of connections of the same and maybe more players, agents.
I have a question regarding this. So I'm with you. This is amazingly powerful model. So there's some results that sort of have taken a look at like who plays computer games with whom, and it turns out that there is sort of a kind of exponential distribution. It's more likely you play chess with your neighbor or somebody down the street than with somebody in Belgrade if you're not a grandmaster. And in Belgrade, it's more likely you play with somebody in Belgrade than with somebody in Berlin. So, do you see differences between obvious, like co-located players? I don't know if you could measure this by IP address or something, who have conversations about the game at the Würstelstand, or at the coffee shop, or versus people who are very obviously like in different continents, for example.
We did an analysis where players are from, and if they tend to form groups, if they are from the same country. And yes, that happens. We also found that we found that time zone matters extremely much. More than nationality. So Australians and Japanese play equally likely together than South Africans and Swiss. And it's more likely that they play together than a Swiss and a Turkish, because there might be 2 hours time difference. But we never did it so systematically that we could publish it. What is also a nice anecdote is that people, I don't know if it's still the case, but they organize in a way that they rent a football stadium somewhere, and then 10,000 meet in person. And they take long trips to meet each other then as humans, not just as avatars, and then they have fun disclosing who they are in the game, etc. Some people even married in the real world.
Oh,
yeah,
it's your fault.
Yeah, Not mine, but Michael Sells. No,
I
he
had
changed.
another question about gender. Sorry, I was wondering if you have done any checks how much people choose the same gender to be represented in the game as they have their own gender assignment in real
There's
life.
huge gender swapping. We did an experiment on this. A little bit unfair, but you could win a prize to go to Mallorca, and you had to send in a mail and also stating your real name. In case you win, that we could send a ticket. And I think 30,000 people participated. And from this, we found that there's a gender swapping rate of about 30%. Mostly males playing female characters. And there's the game is predominantly male. So I think much more than half of the players are male players. Okay.
Did you re-verify your results with the gender regarding the ground truth, whatever that is, or not ground truth, but the real version?
How do you mean?
Yeah, you could do the same gender analysis you did in this plot, for example, with the people who wanted to travel to Mallorca based on their real gender.
But they would not tell us. How would they tell us their neighbors and their friends of friends or their trading partners? We would have to interview them.
No, what I mean, like, but if you have, you could just plug in their real gender into the analysis, couldn't you? And you get the 4 groups. The ones that are male, female, female.
Yeah. We did that. And an amazing thing is that gender swappers behave as the gender they swap to. There's an easy explanation to it. So males in this game are more aggressive, and if you are viewed as a female player, people are much nicer to you. And that's also known from other games.
What a beautiful example of gender being a social construct, right?
Yes. So this slide here is important because females have a much higher, doesn't seem much, but it is much higher clustering coefficient, meaning that females are closing triangles more often than males do. If you have triangles in a network, triangles are always a sign for stability. Yeah. Now, look at this slide. Now, this is a little bit hard to understand what this KNN is. This is the number. So for the friendship networks, this is the average number of friends my friends have. Got it? So I look at all my friends and then I say, how many friends does each of them have? First has 10, the other one has 12, the other one has 200, and etc. And then I take the average of all those numbers, and that's the KNN, nearest neighbor degree. And we see that it's all the same for all networks, except for the communication partners. Males have 20 more. That's huge. What does that mean? Males are connecting themselves to other males that have lots of communication partners. If you think what that means that networks are not structured in triangles, but that they are very fuzzy. You're linking to other guys that are linked a lot, and that does not mean that triangles are formed, but rather the opposite. You're getting like these dendritic networks, which are extremely unstable, but information is flowing very quickly. So these are, it's not meant to be confirming any stereotype or something. So, but if you sum it up in 2 sentences, then it looks like a stereotype. Females are focusing on building stable networks much more than males do. Males seem to care less when by losing a connection, they lose a whole part of their network. They prefer this instability to slow information flow. So we thought that that was important to point out, that this might be, even though gender is of course a social construct, that this might be also at the heart of females being so much underrepresented in top jobs, committees, etc.
Question regarding this. In historical networks, like here's an example that is not gender related, but where you can see similar thing. If you look at the patronage network in say Baroque painting, that is often family based. And so families are, you could imagine them as cliques, like lots of triangles, because everybody in the family is connected to everybody else in the family. And then the artists are sort of like become part of the clique and maybe overlapping cliques. So that is very triangle rich. While in architecture, you have a similar, you have a different structure, exactly the opposite, because the architect has to do with, like if you build a church, like, you know, I don't know, some church in Florence, you have to have lots of business relationships. There's lots of transactions going on because you have to, you know, there's a builder, the mason, the carpenter, the painter. And so you get these more star-like patterns.
Yeah.
Painter doesn't need for, right? So do you see something similar in this, like if you abstract from the gender dimension, do you see something similar where there is a kind of, you know, a more cliquish networking behavior versus a behavior that is, for example, related to campaigns of like one spaceship, like sort of destroying another, where you, right? Is there something like that at the basis where you can, there's a different generating mechanism for the network or something like that, that is more than just the gender?
So we did not find that out. So if there's, you have to think that there's tens of millions of interactions per year. So it's terabytes per year of interactions. So if there's some guys roaming around and attacking others more, and these are predominantly males, that would never explain it. And most interactions are completely unspectacular, just normal. So we also, for these kind of analysis, we took times of war out to see if there is any change. No, there is not. So even in times of war, the changes of patterns that in some domains are huge, do not play any role in these measures that I'm showing you here. In the gender specific behavior. This is also an interesting thing. A link in a network, in a social network, is always bidirectional. In this game, I can say, I like you, I'm your friend. And then I can hope, or then the other person can say, yeah, it's the same, I like you too. Then you have reciprocated the link. So it goes from one direction and then you can reciprocate. How often does that happen? And are females doing it more often than males? And this plot here shows you that females are doing it much more. As much more, 10% more than 10% more. So yeah, I'm skipping those. This is also in line with what we saw in this plot. I'm not going to explain you what the plot means, but we were measuring the time that it takes to reciprocate. In this plot, you see TTR, time to reciprocate. And then we said, if I tell another male, I'm male, I tell another male, I like you, and it takes quite a while before he responds. If a female tells a male, I like you, the male responds immediately.
Mm-hmm.
And wait, what? Yeah, and if a male tells a female, I like you, the response is sometimes very, very slow. So there's maybe something like biology still represented in the players, which we find extremely amazing. We compared this to studies in dating platforms where we see, or where other people see exactly the same pattern. Also, the other thing is true. When one male guy tells the other one, I hate you, the response is immediate. I hate you too. Let's fight it out. There's immediately aggression there. And if a female marks another female and says, I hate you, very often she does not get a response. It's not reciprocated. So conflict is ignored, or the solution for this conflict may be postponed a little bit. It also matches with real world studies. That's always what we have to do. When we find such a thing, then no one believes that this is of any value before you can show that it supports or contradicts other findings. And if we contradict things, again, our stuff is not seen to be relevant. Mm-hmm. But that's, yeah.
I have a question regarding this, sorry.
Yeah.
Can you go back? So, no, the plot where you just were. It's super fascinating. So I'm sort of reluctant to ask the question, but does it strike you as sort of this like onset, which is brutal, right? This kind of preceding the power law, where it's sort of like the low, the immediate stuff is much more frequent than anything that happens later. Is that true?
Yeah. So these are not power laws; these are exponentials.
Okay. Because linear, yes.
Because the x-axis is not logarithmic, and the green things are just the long term. This is after 100 days.
So the long term thing is like some function, but then before there is some, and then there's a much more brutal decay. Like people forget very quickly.
Yes. So we studied two things in this paper. One was the short term. This is in the same day, intraday, where most responses happen, and then the long term. This figure is for the long term. And yeah, on the lower left, you see by plain eye that there's a huge difference in the short term. And also in the other ones, I think in the short term, you always have, maybe not on the daily, no, also on the daily. But then when you start zooming into the day, for example, this aggression behavior, this is all intraday responses.
So would you see that there's like two kinds of memory processes, one fast decaying, and then like once you...
Yes, yes, yes.
Interesting, okay. Thanks.
Could you also tell what's the speed of, you said male to male, female to male, male to female. What's female to female with reciprocity when it's positive? Was it also long or was it quick, female to female reciprocity?
You mean here?
No, in the next one. No, yeah, here.
So in the long term, wait. Female is this pink. For the long-term response, you have this pink, you have to look at this pink.
Enemies remember longer.
Yes, enemies remember much longer than friends. And for friends, males and females, or male, female, forget more or less at the same rate, or forgive.
Oh, okay.
Okay. Another thing that social scientists, sociologists in particular, figured out that humans love to close triangles. And what came out of this in the 1940s was the so-called social balance theory, which was a nice theory, not grounded on any observations until, let's say, the 80s, 90s, and now there's a huge boost of evidence that these guys were correct 100 years ago with their feelings. So it's very often the case that great scientists just feel the right thing without knowing if it's correct. So here, if you have arrows, there's 13 different ways you can connect 3 dots. Okay, that's just the way it is. And with the first 6 triangles we call open triangles because there's one link missing and the other ones are closed triangles. Okay, 7 to 13 is closed. The same Granovetter, in more or less the same year, he said, if we're talking about friendly links, friendship or trading or communicating, that's typically nice, and people do these kind of things, then there's a big probability that if you observe at some point an open triangle, that a little bit later it will be closed. You'll observe that it has closed. So in the game, we can look at the transition rates. We take one time, look how many open triangles are there, or triangles of type 1, 2, 3, 4, 5, up to 13. And then we ask, after 50 days, how many have been closed? We ask this, we count the triangles again and say, how many have now closed? And then you see, for example, that if you go from triangle 6 to 13, 6 is open, 13 is closed, you see a huge number goes from 6 to 13. And how often do you go from 13 to 6? Not very often. So there's a bias. And we can make that bias more explicit. So if you ask, how likely is it to find an open triangle for friends? That's the green line. Just focus on the green dots. How likely is it to find an open triangle of type 1 with respect to pure chance? If the number on the y-axis here is negative, you find it less likely than by pure chance. It's suppressed. And what you see here is that 1 to 6 are suppressed. And 7 to 13 for the friendly interaction, namely friends, being friend with some represented. So this is showing with hundreds of thousands of people that this social balance theory is indeed exactly as they stated it in 1941. And it's more or less the opposite with the enemies. If you have enemies, the enemy of your enemy is not, they are not necessarily enemies. Very often they can be friends. They both hate you. And so.
Sorry, can I just ask another question?
Sure.
I was wondering, so here it seems that over time you can only build links, but can you also remove links in the game?
Yes, you can.
Oh,
you can. So if you do something bad to me, I take away the friendship link and I might put a hate link.
I have another question. Maybe I should ask that later. I don't know. You decide. triangles are just one thing, but there is now this thing called higher order networks, or simplicial complexes, which are, you know, larger molecules of more triangles, open or closed. Did you look at that? Like, what? How about group formation? Is there something? Is there typical molecules we would find in the system?
Yeah, you would call that modules.
Okay.
And then you say you draw up a module. Let's say 5 nodes are connected in this particular way. How often does that appear?
Yes.
And then you do statistics of this.
Mm-hmm.
You can do that. People have done it. But the question is, the question to which I now will come is, how much can I explain with dyads?
Yes.
Or how much can I explain without a network?
Yes.
That's what sociology is. Can you understand without network, without seeing the networks? Then just with one link, that's maybe something that you see in a questionnaire. You never see a network in a questionnaire. And then what you also don't see in a questionnaire is a triangle, unless you ask very complicated questions. I mean, it has become a little bit more en vogue now in the last 10 years that you would, if someone would ask you, who will you vote for, that they ask you, how will your friends vote for? So you need indirect questions, which are, of course, extremely low in quality.
Unit. And
then our question is, how much can you understand with triangles? And let's just see how far we get. And you will see in a couple of slides with this model. Okay, now what do physicists do? They see something which appears over and over again, and then now we need a very hopefully simple explanation why we see what we see. And this is now our model. We have a time step t, the 3 nodes I, j, and k. And we say in the next time step, with probability little r, a number between 0 and 1, we close a triangle between a wedge. And with probability 1 negative r, we don't close the triangle, but we still make a link. That's already a model. Very, very, very simple one. But this is enough to explain 10 facts about social networks. And this is something that you then say, wow, with such an idiotic assumption that we're just triangle closers, we are, as humans, we are more than triangle closers. We all know that. But if we just assume that we do that, we can explain the reason why we have networks that are scale-free, why our clustering coefficient in these scale-free networks is so high, and we understand the so-called attachment kernel. What is that? That is the probability distribution that when you enter a social network, that you link to someone with a particular degree. Forget what I said. It's a thing that you do not get right by chance. So, and we can explain not only for the friendship networks, but also for the communication networks and the trading networks. We understand incredibly much with this super idiotic model. And then we say, okay, we don't look at the 5 at now the quadrangles or hexagons or anything. We don't need. we can explain most of it already with triangles. And you can say, I'm not going to buy it, but it's the basic reasoning. When you look at these triangles in this game, plus means friend and negative means enemy, then you will find that this plus 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 is totally overrepresented. And this, you see in the lowest line is Z, and it's 71. That's the Z score. Are you aware of what the Z score is? This is the number of standard deviations that separate you from pure chance. So if you have a Z score of 1, means that in 68% of all cases, you have an effect, and in 32%, it's just by chance. And if you have 71 here, that means you have 71 standard deviations. This is certainty. Yeah. In physics, you need 5 standard deviations to detect a new elementary particle. The Higgs boson, that's one of the elementary particles, was discovered with a Z score of 5. Okay, so this is, and if you have something underrepresented with a Z score of 112, this is an extremely, extremely strong effect. So we don't have that in society, that one person liking 2 and the 2 hating each other. We don't like that. We hate this situation. If our friends are enemies, then someone is going to drop out of this triangle or change the enemyship to friendship. So this is then the pressure that our friends put on us. Come on, be nice to him again, or something like this. And yeah, so this is like a fingerprint for societies. You find this over and over again. If you look at school classes, if you look at the Pardus game, or if you look at monasteries, that was the classic experiments in the 80s. But if you look at the voting patterns in the US Senate, if you look at the voting patterns of United Nations, of countries which support each other, etc., you find exactly the same things. So the human is kind of conditioned to think along these triangles. And now, just the worrying thing that I announced in the beginning. In the last 5 slides, I show you this worrying thing. Now we say, how can we understand this triangle obsession of the Homo sapiens? And what we all know is that we are forming networks that are not really, but if you want to have the simplest, halfway, more or less realistic model of a society, it's a small world. What do I mean by that? You have your family, and you have contacts in your local neighborhood. Then you have another local neighborhood. These are your colleagues at work. And then you have your friends with whom you do, I don't know, sports or choir or something. You have 2 or 3 areas where you have strong social ties in your life. This is represented here in this small world network, that you have, that everyone has a couple of links to her or his local neighbors. And then there is some shortcuts. These are people that are not necessarily in your sports club, but that you know from somewhere else. And you also interact with them. In the Corona crisis, we have learned a lot about how these networks now really look. And it's amazing that we still don't know more about these networks. But just for a model, they're more or less realistic if you model them like a small world network. And every person has an opinion. We all have opinions on many things. So for example, if we like, I don't know, Putin or not, is represented by a spin upward or downward. And by this arrow pointing up or down. And every person, I don't know how many opinions we have, maybe a dozen, or maybe 100, or maybe 1,000. It's not a million. We have, I don't know, we care about a couple of political things, about social things, what is correct, what is not correct, about the world. It's a set of maybe 100 different topics we care about. There we have an opinion. And each of these opinions is an arrow up or down. If you have a network, and if you have arrows up and down, physicists always think of magnets. And they put down an equation like this. And this equation here measures, in physics, they're measuring energy in the magnets. We're not doing that. We're measuring social stress. And the thing that we assume is that everyone rearranges her or his opinion such that stress is minimized, and we arrange our social networks locally such that stress is minimized. And if you do that formally, you write down such equations. Forget what I said. If you're considering a triangle, on the lower left, there's 2 and 3 are friends and both hate 1. And you see the opinions. One has a different opinion. Then what can happen to reduce the stress is 1 and 2 are changing they start liking each other. Then the stress gets less. And if 1 and 3 also change their enmity, then they reduce stress further. And finally, if 1 is flipping also his opinion, we are ending up in a super nice state. We all like each other and we believe in the same things. Okay, so this is what we can do. We can change our opinion and or our relations. Of course, we can do more as humans than doing that, but this captures a little bit already. And here's now the thing that you can do with this. You have a couple of model parameters. One model parameter is how densely connected is our network. So how many links does every node have? Is that 2 or 3 or 4 or 5? We can vary that. That's the degree again. And the degree here is shown on the y-axis. What this tells you, if you fix all the other parameters, this is represented by this t, everything else fixed. So suppose you're somewhere t is equal 5, then you find a critical k, which is more or less 12 here, where something starts to change. What is this yellow? What is blue? Yellow is the region where your society starts fragmenting. Blue is where society is homogeneous. What do I mean by fragmenting? Fragmented means that you're observing bubbles. In these yellow regions, in the yellow region, bubbles are forming. Bubbles of people that are groups of people that are friends among each other and hate the others. So this is in the fragmented phase, you find islands of friends. And that's in the yellow region, and in the blue region, you have a cohesive phase, meaning you can find friends throughout all of society. Society is connected. There's lots of people who hate each other. That's the narrow lines here. But you can always find paths of people that like each other, that cooperate. So in the cohesive phase, you will always find people that talk to each other. In the fragmented phase, that's no longer the case. There's groups. Within these groups, people talk to each other, like each other, but there is no connection, no positive connection toward other groups. That is fragmentation. And this is happening if social networks are getting too dense. Mm-hmm. And I thought that is disturbing. That's exactly maybe the one single most important thing that has changed over the last 40 years. If you think 40 years ago, in your family, there was one telephone and it was shared with your neighbors sometimes. So you could not make a call if your neighbor was on the telephone. At least in Austria, in the 70s and the 80s, this was the case. I think so in the rest of the world too. Maybe not in the US at that time, but if we're making now with the new method, with the new ways of communication, our networks denser and denser, it must fragment.
So
if the rest is kept the same.
So there's a number of simplifications you make in your model, right? Like one is these up and down things, which is
right.
And so then, you know, obviously that's like Ising model of magnets with up and down spin. Then you ask yourself regarding the percolation, which makes sense if your playing field is basically something like a triangular chessboard that's two-dimensional, and you have these regions, but you have layers. That's like what we talked about for more than an hour. And then number two is the playing field may not be two-dimensional, but it may be multidimensional, and the spins there may not be just two spins, but there may be many different things going on. Like one thing which I would like to put into the discussion, there's this guy Wilfried Trotter, who in 1919, he was a British spy in Germany. He was one of the few people who lived in Germany and Great Britain during World War I. And so he wrote up this thing where he said, in war, society is split. You only have two opinions. You're either for, let me pick an example, for Donald Trump or against Donald Trump. You're for Hitler or against Hitler. While in peace, he says, the only difference between war and peace is in peace, people are interested in many, many different things. And so sort of Yamir Moreno in the last 10 years sort of added this thing that there is this transition between, you know, in the Gezi protest in Turkey, you could be for Gezi or against Gezi on Twitter. While outside in the peace times, people would be interested in many different things, but the different things were integrated in a nested hierarchy. So they had different opinions on, say, cars or maybe musical taste, but they still would agree on, you know, general Turkish agreement that, I don't know, rose water smells awesome, right? And so the question is, if you take your model with the simplifications, this is rather frustrating because we may think, okay, the political parties in Austria and Estonia or in Germany will never talk to each other again. They fragment and then they sort of like go to war with each other. Well, if we assume that there is such a hierarchy, there may be actually a chance to actually construct a world.
Let me
yes.
Say something, because we're mixing two things now.
Okay.
one is polarization, the other is fragmentation.
Okay.
When I talk about fragmentation, I'm not talking about that the whole society is split into two camps where we say Hitler yes or no, or Gezi yes or no. But this is groups of I would say 5 to 1,000 people, bubbles of a size of between 10 and 1,000. Not half of the society, not 10,000s, not 100,000s. So just to what you addressed now was polarization, where we just have two, and of course we were super shocked by our results that we spend now almost 2 years of trying to understand if this result is due to our choice of networks. We take completely different networks.
Yes.
Does it survive? It turns out that yes, we can vary networks by a huge degree and still observe the same thing. Of course, you can overdo it, but then they become so unrealistic that no one would say this is anyhow close. Of course, we don't have one opinion. We have, as I said before, we have maybe up to 5,000 opinions, and they don't have to be black and white. So first thing is, we said we have X opinions, and the X is a free parameter running from 2, that is the from 1, that's what I showed you before, to 10,000. That does not change a thing. So it's robust. Then we say, okay, let's link the different opinions on different networks. About stamp collecting, I'm discussing this with my friends at the Stamp Collection Society, and science I discuss with my colleagues 2 layers of networks, more or less independent. Does not change a thing. If we connect the 2 layers, does also not change a thing. This, and then we say it's not. Let's have not up and down spins, but let's have many different possibilities of an opinion from minus to 1, from 0 to 1, for example, or that is also not changing much. And that's the reason why we say, okay, now we slowly believe that this is a robust result.
And so if you have this result, and the coupling is now happening on the World Wide Web, is that a consequence that the fragmentation is not in resonance with the geographic distribution of the people? So you will have people who have animosities against each other co-located in the same geographic region, right?
With the new forms of communication, geographic location becomes less and less of a necessity. Of course, it's still you're forming those people that you're physically interacting with much more. You're using a lot of communication effort to coordinate things in the physical world. But so for, I don't know, spreading hate or something, or becoming homophilous in spreading hating the same people, as in my group, that is no longer limited to regions, physical regions. A phenomenon that I think is also occurring.
Interesting. Okay. Yes.
Okay, that was more or less it. that's my final slide. And yeah, maybe the take-home thing is that it really might be that by increasing our density of social networks with the new media we have and the new possibilities, it's maybe a tragedy that is unavoidable.
Mm-hmm.
That we become more and more fragmented, and that we have to think of overcoming this. Maybe on inventing new institutional forms to keep up conversations between bubbles that would naturally form. So to put in something unnatural, like an institution that could break this this tragedy.
Dick Helding once said that like society needs fuses because otherwise we become too coupled, right? Like in car grid outages, there's this thing that it's too integrated. So some fault in Hamburg can cause a power outage in Portugal. But if there was a fuse in between, this maybe wouldn't happen. So the question is like, that is almost like asking for, we need societal engineering. Sort of, isn't it?
Yes, it sounds horrible.
Yes.
But yes, or Dirk would call it, we have to empower people with the new technologies to become more democratic again. Yeah, it's maybe the positive formulation of the same thing. But one has to do something, otherwise we're becoming tribes again, fighting each other, or maybe not again, maybe for the first time.
Mila.
Yeah, thank you. Really inspiring talk, and kind of I'm just kind of like thinking, or have you been thinking of looking at some other kinds of data, like historical data, for instance? Because kind of if we think about this fragmentation of the humankind and people, and well, my background, I'm a cultural historian, so that's why I have this kind of thinking. But if you look at, for instance, 100 years back in history, and for instance, I'm coming from Finland, and in Finland we had this really bloody civil war around 100 years ago that kind of like really like divided the whole society into two blocks, and the Reds were in the concentration camps, and so it was really kind of like tragic, like fragmentation of the society. But after that, within 100 years, there has been kind of like more and more this the split has become kind of like non-visible, and I'm just kind of like thinking that would it be interesting to look at some historical developments, kind of like how these kinds of fractions have been overcome earlier, and what kinds of course, within 100 years, there, the telephone became more spread, but of course they were kind of like still really kind of strong division into left-wing and right-wing newspapers, for instance. But then, for instance, the introduction of television kind of was one medium that brought people together, so that everybody was watching the one TV channel or two TV channels and so on. So kind of like these kinds of things, have you been considering kind of like looking at these kind of like historical examples?
I would love to have data on this. And with Peter Turchin, do you know him? Mm-hmm. He's I think, and the hardcore historians, he's a little bit of a controversial figure, but I love talking with him and thinking of how one could get some data. But let me state again. In humankind, we have had this polarization, this split up into two camps, over and over again. For every war, you need a split up or a polarization into two. I think what is new our case now is that people can talk to hundreds of other people on a single day. And we never did this before. A few individuals, maybe big leaders, also 100 years ago, maybe they have seen 100 people on a day. But now everyone can do that. And it's, I think, psychologically just too much for us. We can no longer be open-minded to everyone we talk to. It's such an overflow of having to keep in mind what people are saying that we have to reduce our inputs. And one way of doing it is saying, I like these 15 people and I'm close to them. I just take their opinion. I don't think anymore. I simply have no time. And I have to streamline with these people. Otherwise I get emotionally torn. As a physical being, I hate stress. So whenever someone else is constantly having another opinion, let's kick him out of our group. Otherwise we cannot handle it. So, and this leads to not fragmentation into 2 camps, but into thousands of camps. And that's why I say one has to distinguish very clearly between this kind of fragmentation, this bubble forming, it's like bubbles in a Coke, and polarization, which is like vinegar and oil in a salad dressing. And I think this fragmentation is a new phenomenon. And maybe the explanation is just the cell phone and the internet.
There's 2 questions, one by Nikita, who didn't say anything yet, and Viuna again. Okay, Nikita.
Yeah, thank you very much for the opportunity to ask a question. Thank you very much, Stefan, for your lecture. I was actually first introduced to works back in 2016 by Professor Peter Slot when we were working on the comorbid diseases networks. And since then, I'm trying to keep up with the biomedical domain, and I noticed that the recent advances there is lying in the field of new graph neural networks models. So which somehow combine the network representation and also the power of machine learning tools. And what we've discussed here on the first slides, you were talking about the common neighbors of a few nodes, and that is actually, I guess, one of the ways to solve the link prediction problem within a graph, to see for the common neighbors. And somehow graph neural networks also solves link prediction task very efficiently, and actually make it more accurate than existing methods. So my question is, what would be your opinion on actually using graph neural networks in cultural domain? Does that would benefit the fact that we would combine the relationship between different entities together with actually working directly with some text and images as a node features? Or maybe it's just a new fancy deep learning thing which would not give a huge improvement?
So I think there's a huge potential for machine learning techniques and link prediction. And I mean, this link prediction is the key question. That's the royal question, kind of. If you can do link prediction, I mean, a little bit better than others can do, you can change the world, I guess. And one way of link prediction is triadic closure. That's maybe, yeah. In the way I formulate it, it has nothing to do with neural networks or machine learning, but I think to understand better, and that relates to a question earlier, how other structures, how other features, and by features you could mean or understand other network motifs, how you can use network motifs as features that help you with link prediction, where the main driver is maybe triadic closure. I think the mix of this could be tremendously potent.
Thank you very much. This is certainly very, very interesting. There is 2 more questions and we got 6 more minutes, so I'm not asking anything more. Mark.
Yuna was first, actually.
Okay.
No, go, Mark. I asked heaps of questions before.
Okay, I'm not sure if my question is repetitive because I'm not sure I understood the answer to Max's question before about the hierarchicality. So are the well, in one sense, is there like sort of hierarchicality between the polarization and these fractions, and how do you see actually these fractions forming hierarchicality between themselves? What is your take on it?
So we did not study hierarchicity or hierarchicality within these bubbles. We did not look at anything there. We looked at hierarchicity when we were looking for elite structures in the whole network, in the whole game. We tried to identify those players that are making a difference to the world, to the Pardos world. And there we tried to reconstruct hierarchical trees with a new method that we invented for this.
Mm-hmm.
A little bit like K-core clustering, but a little bit generalized.
Mm-hmm.
Yeah, I'm sorry. Would be, of course, it would be super interesting to see who is the leader, who are the opinion leaders, if there are any in these bubbles.
So maybe one should ask you a different way. Like the question is, like there's a social hierarchy, but there's this other. You could think maybe of like something like a bifurcation of fragments, which on one end would be one, and on the other end, every individual would be a fragment. And so is there a gradient in between? In other words, that I think is sort of like where Mark and I were sort of directed, right?
Yeah, closer.
So that would be a very interesting thing to study. I would like to, like, before I give the last question to Liuna, say also the thing you mentioned with not having binary things that's related to this, but gradients between like very friendly, very negative, or maybe even multidimensional sort of features. There's this thing called semantic differential, which is around since the 1950s. Which is, I think, lends itself very nicely to combine here. And so the question is obviously the neat thing about what you showed is that there is sort of there's a permutation space. There's sets you can count. Well, if you have more, if you allow for more complicatedness, then obviously your combinatorial space explodes, and then you're back to square one with like humanities in essence. Okay, so Liuna.
Thanks, Max. And thank you so much for the presentation. It's really inspiring. But I had a question based on the whole thing, I guess. In the beginning, you mentioned that when we study networks, especially social networks, the whole context of the society is very important, and that basically we can only analyze them when we have information on the full society or the full network. Now, in my own work, I work a lot with collaboration networks in film production and TV production. And of course, when you work with databases as such, you have information on some connections, but you will never have information on all of the connections that are present in the network. And I was wondering how much these concepts that you introduced and different statistics you computed could be applied to these real-world networks to understand them. And I was especially interested in the slide that you showed on open and closed triangles. And I was wondering, let's say, if you had different real-world networks and you looked at the presence of open and closed triangles, based on that, could you perhaps evaluate them, how hostile they are, like either friendly or either friend networks or enemy networks, something like that? I don't know.
So maybe, thank you very much. This was one of the most important questions we have. So one interesting thing I could add is, like, in what we know in culture is that many of these networks are typically sampled in a snowball manner. And if you do that, you end up with a lot of like peripheral nodes having lots of fans, meaning lots of open triangles. So the question very simply is, how do we deal with that?
Depends on the question.
Okay.
So what we are a little bit known for is to try to give answers to systemic risk. What is systemic risk? Mm-hmm. And it's to a large extent the network property. So here the network is not social relations between people, but lending and borrowing relations between banks, for example. And if one bank is killed, how does the damage spread over this network? And what we have learned there is two things. If you are missing one link, you can end up with a completely different result. So this is one of the messages that we know more and more for complex systems. Very often, for many questions like systemic risk, details matter. It matters that you know the network exactly and not just more or less. Of course, we're still living in a century where we never have all of information. So you can take two paths. One is I prepare for a world where we have all the exact information, which will be next couple of decades. In the banking system, for sure, everything will be there at a super high precision. Maybe in medicine also more and more that we can count molecules within individual cells. That's a possibility. So, or you focus on reformulating questions in a way that the partial knowledge of networks will help you also. But for this, then it's necessary to know how much partial information will influence your results. That's what we are doing often, very often, that we assume that we have the full information for a particular question. We have a network, we give an answer for that network, and then we destroy the network in a way that we think that the real data is actually looking like. So we take out parts of the network, or just, as you said, we take away the links from the leaf nodes, so that we have open triangles there, and then we ask, now, how does that change the true result? With what kind of errors do we have to live with? And for some questions, the effect is minor, but for other questions like systemic risk, can be dramatic. And especially when you have triangles playing important roles. When you're closing So, are you a physicist? No.
No.
Mathematician? Also not. No. If every network you can represent in a matrix. And if you have, then there's some mathematical operations you can do with matrices. And one of these operations is to compute the eigenvalues. Doesn't matter what that is. You can distill one number out of a network, of a matrix. And depending if that number is larger or less than 1, the dynamics that is driven by your network or that is related to this matrix is completely different. And very often by closing triangles in a network, you can push that number over 1. So changing, that means you change with a very little change in the network, you change the dynamics of the whole thing completely. That's
Thank you very much.
Yeah.
This was awesome. I'd like to say 2 sentences at the end. One, which says, there is a new sociology, no social science. We don't ask questions, we observe. Nice. We just watch. That's very much where a lot of us are coming from. And the second one is what you just said. That's, I think, what's the really the premises for collaboration between the spectrum of already existing cultural fields and you know, complexity science, sociophysics, and so on. Because there's these mathematical relations like matrix decomposition into eigenvalues, models, but also the dealing with uncertainty, which, if you're frank, the humanities always talk about the fact that they wanna sort of, you know, they think they have it covered because they deal with the uncertain data, but our tools are not very good. And you know, people who study exoplanets have better tools to look at like shitty samples of time series. And we should adopt them. That's sort of the key idea. And we should adopt them not only for time series, but all sorts of other stuff. So thank you very, very much. This was exciting. And I hope everybody else agrees. There was lots of clapping going on. So I think everybody does agree. And so we will stay in contact, I assume.